This is a podcast on writing Lewis structures for ionic and covalent bonds. And let's review just a little bit. So ionic bonds are bonds that have a metal and a nonmetal, so that would mean a cation and an anion. And covalent bonds are usually between two non-metallic elements, and so we don't really call them anions or cations at all. We just say they're two non-metal elements, and that's from the upper right-hand side of the periodic table. And we're going to look at ionic bonds first. So with ionic and covalent bonding, let's do a little bit of a review. Ionic bonds are combined of metals. That's why I'm circling here. These are, in general, the metals. Some of them have different group names. And to finish the ionic compound, it's combined with a nonmetal. In general, these are the nonmetals. So again, it's a metal and a nonmetal. The metals form cations, hence that's why you see like a +1, a +2. And they combine with a nonmetal, and you can see the charges on there because they take the electrons from the metals and become like a -3, a -2, a -1. And there's a transfer of electrons. And we note that differently than we do covalent or molecular compounds. So let's talk about compounds with covalent bonds. They would be two or more of these elements over here in the non-metal range, and they share electrons. Sometimes they share them equally, and sometimes they share them unequally, and that's called a polar covalent bond. So again, we have ionic, which is metal and nonmetal, and we have covalent, which are two of these from this side. So let's try drawing some Lewis structures for ionic compounds. And again, that's going to mean that we have a metal and a nonmetal. And we'll start with a simple one. We'll start with lithium and fluorine. Do you like those two arrows? That was pretty impressive. So lithium and fluorine. So lithium is Li, and it has one valence electron. How did I know that? If you go to the periodic table and you look at lithium and you look at that very bottom number, it's 1, or a simpler way is it's in group 1, meaning this whole column here, so it has one valence electron. And I drew it with one dot. Do you like that? One dot, and you could have drawn it on any side. And then we said fluorine. So fluorines are nonmetal, and fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. My children would tell me to shut up. And how do I know that there are 7 dots there? If you look at fluorine over here, the bottom number is 7, so it has 7 valence electrons. And if you want the real technical speak, it's because it's an S2P5. The 2 and the 5 make a 7. Or you could look at that 7 in front of the A. That means that it has 7 valence electrons. All these elements in that group. Is the last chapter coming back to get you? Possibly. So what happens here? The lithium is the cation. It really gives up the electron. And who does it give it up to? It gives this one electron up to fluorine. And when it gives up the electron, you write Li. It loses that one electron, so it becomes a 1 plus. Ta-da! And then fluorine takes that one electron. Let's make our periodic table a little bit smaller. So fluorine takes that electron, had 1, 2, 3, 4, 5, 6, and then it had that 7th one up there. And then, so that electron is going to go there. It doesn't really matter what side, but it goes in there somewhere, somehow or another. And since it gained an electron, it is now 1 minus. You always put these brackets around there. I don't know why, but you do. I always think of it as the rage in the cage. And now it's a -1. And if you think about it, a plus and a minus add up to neutral, which is if you were to write this as a compound, you'd write LIF because there's just one of each, and it would be neutral. And neutral meaning if you had a superscript up here, it would be a 0, but we never write that 0 because, frankly, that would look really weird. So in your final answer, you would have Li plus and F with 8 dots around it and a minus. So let's try another ionic compound. Let's do sodium, and we'll do chlorine. So sodium chloride, that's table salt. I'll ask you that all year long. So sodium and chlorine. So in your head, you really visualize how many valence electrons does sodium have. Sodium has 1, and where did I get that from again? If you look at sodium in this row here, it has 1 valence electron, so it has 1 dot. And then we move to chlorine, and if you find chlorine way over here, it's in the 7th group, so it has 7 dots. 1, 2, 3, 4, 5, 6, 7. Why did I put them there? I don't know. I just did. It apparently made me feel better. And what happens is that sodium loses its one valence electron over there and gives it up freely. Actually, it doesn't hold it in very tightly. So sodium becomes a plus, and then the chlorine has 1, 2, 3, 4, 5, 6, 7, and it gains that extra one. We'll put it in yellow. It doesn't have to be a different color, and it doesn't have to be big and look like a squished grape, but it does. But you can't forget the brackets around the Cl and then the minus. So you have to have that plus there, and you have to have that minus there, and you have to have the 8 dots around the Cl, and that is your final answer right here. That is the Lewis structure for an ionic compound. Now let's do one that's a little more difficult. Let's try sodium, and it has 1 dot, and we'll do sulfide. So sulfur, if you look over here, it's here somewhere. 1, 2, 3, it must be over here. Sulfur is in group 6A, so it has 6 dots. 1, 2, 3, 4. Let's put it up there, 5, 6. So the nonmetal always wants to have 8. Boy, I'm making some antenna there. The nonmetal always wants to have 8 dots around it. And so if we just have 1 sodium and 1 sulfur, is this 1 electron going over there going to fill it up? I'll answer the question for you. It's not. You need another sodium with another dot that would go right there. So in essence, you have 2 sodiums, so you'd write 2 in A. In each one of those, sodium's lost a plus, so it's not 2 plus. In essence, you do it in your head, 2 times that plus makes 2 electrons lost. Now we have to finish this. Our sulfur now has 8 dots, 1, 2, 3, 4, 5, 6, 7, 8, and we put a bracket around it. And it was just 1 sulfur, and the 1 sulfur gained that electron and that electron. The 1 plus 1 is 2, people. Oh boy, squeeze it in here. A 2 minus. So this would be your final answer for this one. You'd have to have 2 sodiums and 1 sulfur, and the sodium is a 1 plus and the sulfur is a 2 minus. Let's try one more. Let's do magnesium, and magnesium is a 2 plus. Sorry, I'm getting way ahead of myself. Magnesium has 2 valence electrons, is what I really meant to say. 1, 2. And let's do phosphorus. Phosphorus is in group 5. It has 5 valence electrons. 1, 2, 3, 4, 5. So how many empty spaces does it have? It has that one, and that one. So we'll start doing our little electron giveaway dance. So that one goes there. That one goes there. But all of a sudden we have this empty spot that we have to fill up. So maybe you have a whole bag of magnesium and phosphoruses you can add to make them in the correct ratio. So then this one goes there. Ugh, nuts. All of a sudden we have an extra dot on the magnesium, so let's just pull out another phosphorus from our bag of chemistry tricks. And, oh, what did I say? 1, 2, 3, 4. I got a little excited. I put too many dots. I gave you too much money from the bank. And all of a sudden now, that dot's going to go there. Oh boy, let's pull another magnesium out of our bag of chemistry tricks. I feel like Felix the cat. So that one is going to go there. Oh, this is perfect. And then that one's going to go there. So how many magnesiums do I have? Let's change color. So my magnesiums, I have 3 magnesiums. And the charge is a 2 plus because each one of those magnesiums lost 2 electrons. And then my rage in the cage is, this is going to be the skinniest P you've ever seen. And each P has 8 dots. So really and truly the trick is anything you put in the brackets over here always has 8 dots. And then count back how many P's. You have 1, you have 2. So you're going to put a 2 in front of there, in front of those brackets. And then you have to put the charge on the P. And the P, each P gained 3 electrons. Make that 1, please. And it really goes on the upper right hand side, but I had to squeeze it in there on the screen, so it's a 3 minus. So you have a 3 Mg2 plus, a little bit of space, a 2, and in the bracket is a P with 8 dots around it, and the brackets and a 3 minus. And then you multiply 3 times 2 is 6 plus, and that would cancel out 2 times a 3 minus. Oh, this is a beautiful thing. So the ratio is 3 of these to 2 of those. So I don't really need to see your work ever. This is what I'd want to see as the final answer. So now we're going to try doing a Lewis dot structure or diagram for covalent compounds. And remember that covalent compounds are items that are two nonmetals from this region up here. And let's start with, I don't know, we'll do CO2. So we're going to start with C, and we're going to start with two O's, and we don't look at the valence electrons on these at all. And I'm going to walk you through this bizarre process that works almost all the time. So we're going to do CO2. And we have to figure out how many bonds there are. So really and truly, the first thing I do is I just draw, it's called a stick structure. And since there is one carbon, it's probably in the middle, and the oxygens are probably on the outside, and they have to be attached by at least single bonds. So notice in the ionic bonds there were no lines showing shared electrons. These lines show shared electrons. So there's at least a single bond, and that's why I drew the single bond. There might be double or triple bonds. So this is how I go about finding out how many bonds there are. And I use the letter P for perfect, and then I do A for actual, and I do the P's on top and the actuals on the bottom. The P is always a bigger number, that's why it's on top. So I go to carbon, and I look at my periodic table, and the perfect, P stands for perfect. Perfect is if carbon were perfect, if it were to gain the correct number of electrons to be perfect, it would be 8. It's almost always 8. So there's 8 for carbon, and then oxygen, if it were to be perfect, it is 8 also. The only one that is different is hydrogen is 2, and boron is 3 or 6. Anyway, so I have one carbon, so that's 1 times 8, but I have 2 oxygens, so I need to multiply that by 2. And then I add those two things up. So 2 times 8 is 16. 16 plus 8 is 18. It should always be a whole number. And then what does it actually have? So if I go and look at carbon, carbon actually has, look at that bottom number, 4 valence. Oh, mamma mia, where'd you go? 4 valence electrons. So it actually has 4. And if you look at oxygen, oxygen on here will say that the bottom number is 6, so it actually has 6 valence electrons. But again, there's 2 because of that 2 right there. There's 2 oxygens. So I will do 4 plus 6 times 2. So 6 times 2 is 12, 13, 14, 15, 16. That bottom number should always be smaller. So this is a trick. I know it seems like it's coming out of the deep ocean. Maybe it is. And so you will do 18 minus 16, which I am confident that you can do. And 18 minus 16 is 2. And then you divide by 2. You always divide by 2. That's how many electrons in essence you have, and then when you divide it by 2, it tells you how many bonds. Oh, this can't be right. Let me say it's cracked up. If you haven't figured out by now, I can't add and multiply. I am in some other freaky land of not being able to do that, and so what I really need is, I can't erase this number, so I'll just cross it out, is that number isn't 18, it's 24, people. So 24 minus that 16 would give us 8. I'm running out of colors here. 8. And then you do 8 divided by 2 is 4 bonds. So it should have 4 bonds. So far I have 1 and I have 2. And I could put a 3 and a 4. Or I could do 1, 2, 3 to that one and 1 to that one. Or I could do 1, 2, 3 on that side and 1 to that side. So there's 3 different ways I could write this. Wow. But I'm not done yet. I have to go back to this actual number, 16. It's very important. And all my electrons have to add up to 16. What do I mean by that? So that line represents 2 electrons, and each of those lines represents 2 electrons. So 2, 4, 6, 8. I'm not quite yet to 16. And what you have to keep in mind is that every element that we have here wants to have 8 as their perfection. Who doesn't want to be perfect? So this oxygen needs 2 there, 2 there, 2 there. They always go in pairs. They're called lone pair electrons. So we have that single bond, and then 2, 4, 6, and then that makes 8. Who cares about the Fitbit? And then if we look at the carbon, it has 2, 4, 6, 8. Carbon is done. It's cooked up to 8. this oxygen has 2, 4, 6. It needs 2 more, which is 8. Now if we go down to this next one, we have to do 4 on this one. I just put 2 on each side. Carbon, again, is finished because it has 2, 4, 6, 8. And then we need to do the oxygen, 2, 4, and a 6. And it's so yellow. Give me some black ones here. 6 and an 8. And that last one, it is the reverse of that top one. So we'd put 2 there, and then we'd put that many sets around that one. So let's look at one individual one and make sure all of our dots add up to that magic number 16. Here we go. 2, 4, 6, 8. Who do we appreciate? 10, 12, 14, 16. Woo! We did it. So I picked a really hard one to do for the first thing. So let me recap covalent bonding really quick. So I'm just going to put some covalent compound, 2 nonmetals together. And what I do is I do a little trick. I do the perfect actual electrons on the top. I do what they actually have according to the periodic table. And let me do this real quick. So perfect would be 2 times 2, because there's 2 of those, plus the oxygen should be perfect at 8. Hydrogen is the only one that's perfect at 2. Let's see if I can add this time. So 8 plus 2 times 2 is 4. That's 12. And this one, hydrogen's actually 1, but there's 2 of those hydrogens there. Plus oxygen, which is, look at the periodic table, the bottom number is a 6. So 6 plus 2 is 8. And you get that number 8, so you do the perfect, and you have the final number there. You do the actual valence electrons, you have 8. I put a little line underneath there. I subtract the 2, so 12 minus 8 is 4. Am I ever going to ask you for this work? No, I'm not. And then what you do is you always divide by 2 to split up the total number of electrons. And so 4 divided by 2 is 2. So 2 bonds means 2 lines. So with H2O, the O is probably in the middle. The single thing almost always goes in the middle. So we have H and an H, and we already have 2 bonds. We have 2 bonds, we're done. But then we have to go back, remember this part, and have all of our electrons add up to 8. My H doesn't look very good. So when I look at my H, I go back and I remember that when H is perfect, it is a 2, so it already has a 2 right there. And my other H is the same. It's perfect also because it has that 2. And the last part I really need to get up to is that 8, like I said. So they're going to go here. Oxygen needs 4 more, or 2 more sets. So it has 2, 4, 6, 8, and that adds up to the 8. And that is the Lewis structure for water.